Okay, welcome to today's class. So, today we shall be discussing about network protocols. So, we essentially have been studying about various primitives in cryptography, but this is the kind of first objective or first place where we will try to combine or use the cryptographic primitives and try to build up a protocol for security. So, the protocol essentially there are certain objectives in a protocol. So, the first thing is to understand what are the objectives in a protocol. Okay. So, and there are various kinds of protocols also existing in the literature. So, presently we shall try to understand a category or a type of protocols. Okay. So, let us try to understand what are the objectives that we shall be considering in this class. So, first of all we will try to essentially understand what are the important and implicit assumptions which are there in a cryptographic protocol, or what are the requirements from a cryptographic protocol. So, we shall actually consider a 5-stage design of a 3-party protocol for key establishment, where we shall see that some of the important concerns are confidentiality, authentication, and the fact that an adversary can be an insider too, and also about the replay of old messages. So, these are some of the things which some of these things we have actually seen previously, but we shall see them again in the context of a protocol. So, note also another thing that we essentially will be considering a 3-party protocol in this case, but there are various protocols which can also be 2 parties, but the objective of this particular discussion is to understand the basic properties which are required there in a protocol. Okay. So, we shall be also understanding or discussing about Needham-Schroeder protocol and the Kerberos protocol, which are very famous protocols in this domain, and we shall conclude with some discussions. So, the first thing is that what are the keys which exist in a protocol. So, there are essentially 2 types of keys which exist, one which is a long term key and the other which is a session key. Now, the long term key is generally generated by a more costly process, which is could be like Diffie-Hellman, and it is stored in protected places and it is generally well preserved. The idea is that the cost of a long term key is quite high. So, therefore, it is probably determined or established by a public key exchange, which is actually which comes with an accompanying cost. I mean, there is a cost on the network, there is a cost in terms of computation. So, therefore, the protocol or the systems will try to protect these long term keys and change them less frequently. As opposed to that, we have something which is called as a session key, which is actually used to change per session and changed much more regularly. So, the idea is that these session keys are actually more vulnerable or more prone or more subjected to cryptanalysis, because since what we do essentially we generally set up or use a public key protocol to set up a long term key and then use this long term key to generate session keys. Now, this session key is used for bulk encryption, like for bulk data encryption, like when we are actually using maybe a private key or a symmetric key algorithm, and the idea is that therefore, the observer or the attacker actually sees lot of ciphertexts which are generated or used by the session key. So, therefore, the session key is actually the prime target of a standard cryptanalytic approach. Okay. So, therefore, that implies that the session key needs to be changed more regularly. Okay. So, in our case also we will see that we will assume that there are some long term keys which are being already prepared or stored in a tamper proof place, and it is used to generate the session key, which is actually something sometimes also called the ephemeral or the short lived key. Okay. So, therefore, the context that we are considering right now is actually there are 2 parties or 2 legitimate entities, that is Alice and Bob, and there is a third entity which is the trusted server. So, the trusted server actually has got knowledge about Alice and Bob, and it tries to perform a key establishment between A and B. So, therefore, the objective of A and B is to essentially establish a new session key called KAB. Okay, and this KAB will be used for further communication between Alice and Bob, right. So, that is the basic context, and the objectives of the key establishment protocol is that at the end of this particular protocol, KAB should be known to only AB and of course S, because S is the trusted server, and also A and B should know that KAB is newly generated, that is KAB should not be an old key, it should be kind of a fresh key. Okay. So, these are the 2 primary objectives behind this protocol. Okay. So, now let us try to build up this protocol and try to build up this protocol in stages. Okay. So, the first attempt could be a very simple attempt. So, it could be like that is this A and B which are actually the legitimate entities, and S is the trusted server. Okay. So, what A could do is that A could request S and say that I want to generate a session key KAB which I will use for my further communications with the party B. So, in a very naive situation, S can directly send back KAB, and you know that A can again send it back to B saying that okay, this is the key which S has sent me and we will use it for further communication. Now, obviously, you understand that this is a very naive protocol, and therefore, it can be subjected to various kinds of attacks. Okay. Now, the attack we can, if we try to kind of write it in the form of a security assumption, we know that this protocol is weak because we know that the adversary is able to eavesdrop all the messages, that is these channels are not at all trusted channels, right. So, since these channels are not trusted channels, an eavesdropper can simply observe this traffic KAB and get the session key. So, of course, this is not what is intended. So, the obvious idea is to use encryption, right, and that is the second attempt. So, what we do is that we send again A sends to S that it wants to communicate with B, and so it sends this identifier A and B. So, note that these identifiers could be in the form of maybe your IP address or anything which indicates the particular user. Okay. So, we are considering these two entities, and A and B are unique identifiers in the network for the users A and B, right, and which S also is aware of. So, therefore, S is a trusted server. Now, what S does is that S takes KAB or generates somehow a KAB and encrypts it by the long term key. So, as we told that the long term keys are there. Okay. So, the long term keys have already been established by some Diffie-Hellman kind of technique which we have seen in our previous classes, and KAB is communicated to A, and of course, this is encrypted by KAS and KBS which are long term keys. So, therefore, you know that S is aware of the fact that A and B are legitimate users, right, and therefore, it has from some database it retrieves the value of KAS and KBS and encrypts it and gives it back to A and B. So, now A also has the long term key. So, A has a long term key called KAS, and therefore, it can take this traffic and it can decrypt this and obtain the value of KAB, right. And what it does is that the other part of the traffic, that is KAB which is encrypted by KBS, it just communicates with a ciphertext with along with the identifier that is A. So, from the face of this we know that the previous problem is alleviated, that is the key is not being transferred in clear, right, and also B is aware of the fact that it is establishing the key with A. So, this is a better protocol definitely like than the previous protocol, but still it is vulnerable to attacks. Okay. The attack is possible because of this assumption which is quite practical in a normal network, is that the attacker is able to alter messages using any information available. It is also able to reroute messages, generate and insert completely new message. So, which means that the attacker is not necessarily a passive attacker, but it can be an active attacker as well, right. So, it is capable of altering messages, it is capable of inserting new messages, and it is kind of it is just not passively observing the network, but it can also inject some other extra information into the network. Okay. So, therefore, what happens is a possible attack like this. So, let us consider that there is an adversary called C, and we essentially see what C does is this, that is when A is being when S communicates to A, this encryption, that is KAB encrypted with KS and KAB encrypted with KBS, and therefore, we know that A communicates or rather tries to send to B KAB which is encrypted by KBS, okay, and A. So, what C does is that instead it takes the first part, but modifies the second part and makes it something like D, right. So, what is the problem? The problem is B thinks that B takes the first part and of course decrypts it and thinks that the KAB key is actually meant for communicating with D. So, therefore, we see that A and B. So, therefore, if you remember the objective of this protocol, the second objective was that at the end of the protocol both A and B should be convinced that they are establishing a new key and should know with whom they are communicating, right. but in this case there is a problem. The problem is that B thinks that it is communicating with D, and therefore, what may happen is that what may happen is that B may leak some information which is meant only for D to A, right. So, because B may actually end up in communicating things which are actually meant for being only sent to D, because it thinks that it is using KAB for communicating with D, can actually end up in leaking those information to the user A. So, therefore, you see that this is an example where C or the adversary does not necessarily know the session key at the end of the thing, but it has definitely sabotaged the intention of the protocol, right. The protocol was meant to establish a key between A and B, and it was also meant to make sure that A knows that it is communicating with B and B knows that it is communicating with A, right. So, therefore, this is a vulnerability of this protocol. The other possible vulnerability could be this protocol, where here C is not necessarily an external user, but it could be an insider also. Okay. So, what may happen is that C knows, or rather C has got, S knows that C is a valid user, and therefore, there is a long term key which is meant for C also in the database of S. So, there could be like a long term key which is KCS, which is maintained in the database of S. So, when A sends to S A comma B, C may come in between the traffic and may modify the traffic A comma B to A comma C, right. And what may happen is that in this process S will understand or think that it is actually communicating with it is actually supposed to generate a key which is meant for communication between A and C, and therefore, what it will do is that it will generate a key or a session key which is KAC and encrypt it with KAS, which is for A, and also the other part will be with KCS, which is meant for C, right. And now, when this particular message comes to C, what C will do is that it will take the second part and decrypt it with KCS, because it has got KCS, and obtain the value of KAC, right. And therefore, next what it may do is that it may benignly or harmlessly just communicate this traffic to A. Now, A has got no way of understanding that this is not what it intends, right, to receive, because you see that this is also nothing but a bit string, this is also nothing but a bit string, right. So, therefore, there is no way of that A can actually understand that this is not what is intended to be sent. Okay. So, therefore, it will take the first part and it will decrypt it by KAS and will communicate back the next part, that is KAC encrypted with KCS, and send it to B, right. But note one thing, that it may happen that if you send this part to B, then B will decrypt it by its own key, right, because B has got KBS, and what may happen is that it may get something which is completely arbitrary, right, and therefore, may not be there may be a problem. So, what C may do is that C may instead come and block that traffic and block it from being sent to B. So, therefore, you see that B has got no way of understanding that there has been a problem, and at the end of the protocol what is happening is that A, who thinks that it is actually communicating with B, is actually communicating with C. So, C is in this case masquerading as B to A. Okay. So, C is actually masquerading as B to A, and therefore, it is obtaining all the information which A actually sends for B, right. So, therefore, you see that A thinks he is communicating with B while he is actually communicating with C. So, C knows KAC and thus can masquerade as B to A and obtain all information which A sends for B. So, therefore, you see that the assumption is that insiders can be attackers or they can combine with outsiders to pose attacks. So, therefore, the attacker need not be an external agent, but could be an insider who has got a long term session key established with the trusted server. So, what is the implication of these two protocols, or rather these two protocol attacks? The implication is that we have to use the identifiers A and B inside the encrypted packets. Okay. So, therefore, therefore, the idea is that the encryption algorithm in this case has to be used for data integrity and not for confidentiality. So, previously we have seen that we have used the encryption algorithm for confidentiality, that was the first step, but in this case we are actually using the encryption algorithm for data integrity, because we want to convince B that it is actually communicating with A and I want to convince A that it will actually communicating with B, right. So, therefore, in this case the idea is that A sends to S again A comma B, but when S sends back a message, it takes this B and A and puts it in the plain text and encrypts it along with KAB. Okay. So, therefore, you see that the identifier is encrypted along with the session key which has been generated. Okay. So, now you see that the previous attack will not work, right, because if C sits in between and modifies it, then it cannot generate because when the moment A will decrypt it, it will immediately understand that it is B with whom he is communicating, right. So, therefore, you see that if C actually poisons or injects a wrong message, that will be immediately be detected, right, and therefore, the previous attack will not hold. Okay. So, therefore, what A does is that it just takes the second part, that is KB and A, and encrypts it, I mean which has been encrypted by KBS, and just relays it back to B. So, therefore, the previous problem is quite nicely solved. Okay. So, here we see that the confidentiality is achieved because since encryption has been used, an adversary cannot eavesdrop, authentication has been enforced because an adversary cannot actually alter the messages, right. But then we again have a new security assumption. The assumption is based upon the fact that there could be a scenario where the adversary is aware of previous session keys. Okay. So, it could be like an adversary was actually a member of the group at some point of time, but has left that group. Okay. So, now when again this attack, the moment when we are considering this particular protocol, at that point this adversary is actually outside the group, but it knows a previously generated session key. So, these are typically called as replay attacks. Okay. So, let us again consider this particular protocol in the light of this kind of scenario, right. So, let us consider that there is an adversary C which does this. So, what C does is that here C is replaying messages which it has actually observed in an old run of the protocol via eavesdropping. So, it could be either eavesdropping or it could be like it has been a part of the previous protocol. Okay. So, however, A has got no way of detecting this, and let us see what happens. So, therefore, A sends this message A comma B to C, and you remember that C was actually, or rather A thinks that it is actually communicating with S, the trusted server, but instead C comes and receives the message, and instead of allowing that message to go to S and come back to S, it actually replays an old observed message. The old observed message is what? It is K dash AB, which is an old session key, right, and which has been encrypted by KAS along with the identifier B, and K dash AB along with the identifier A, which has been encrypted by KBS. So, now you note that this is an old traffic which has been generated. Okay. So, this message is being communicated back to A. So, what A does is that it just takes the second part and communicates and sends it to B. Now, what is the problem? The problem here is that C has actually knowledge of this K dash AB, which is an old generated session key, right, and therefore, the session key which has been actually established between A and B is actually already known to the adversary, right. So, therefore, in this case we are not able to enforce the criteria that we want A and B to establish a new key and not an old key, right. So, remember that one of the objectives of our protocol was that A and B should actually generate a new key and not an old key, a fresh key, right. The reason is this, because it may happen that an old key has leaked, right, and if the old key has leaked, that should not actually affect my communication or the security of the communication at this point, right. So, therefore, here the problem is that you know that A has got no way of detecting this, right, and ends up in establishing an old session key. So, you also can note that here C may not even know the old key. Okay. So, we are considering the fact that okay, C may not even know the old key, but then again it has sabotaged the basic purpose of the protocol. The purpose, one of the important purpose of the protocol was establishment of a new session key. The reason being very simple, that is, if you ensure that always the old session key is or the old session key is generated and a new session key is not generated, then the eavesdropper can actually obtain lot of cipher texts which are being generated by the same old key, right, and then it can actually try out various other cryptanalytic methods and try to actually get the information about the key by some other means, right. So that is the basic purpose of changing the key, right, because we want to ensure that if I change the key, then the cryptanalyst is not actually getting access to a large number of ciphertexts which have been generated by the same key, the same session key. So if in this case an adversary ensures that an old key is being generated and a new key is not allowed to generate, then that is also we will say as a vulnerability of the protocol, a weakness in the protocol. Okay. So in order to solve this kind of protocol attacks, the thing which is used is some concepts like n1s or nonce, okay, which are actually nothing but some randomly generated fresh entities, fresh bit strings. Okay. People also use timestamps like that, maybe the time of the day, right. So there are various other methods, but so the idea is that an n1s is being generated, which is nothing but a random value which is generated by one party and returned to that party to show that a message is newly generated. Okay. So what may happen is that A sends to S A B comma NA. So the previous thing you see that it was A comma B, now we have added a fresh n1s which is NA. Now what we do is that when S sends back the message to A, it takes the key KAB, which is the session key, along with B, along with this NA, which is again sent back, so that when A decrypts it, it gets back this NA and knows that it is the new thing which has been generated, right. So therefore the message which has been received back is actually corresponding to this message, and hence it is fresh, right. And along with it is this thing, that is KB comma A, which has been encrypted by KBS, and the whole thing has been encrypted by KAS. Okay. So often this small entity, this KB comma A, which has been encrypted by KBS, is called the ticket. Okay. So it is called the ticket, like A wants to communicate with B, but in order to do so, it actually obtains a ticket from S. Okay. So it obtains two things, it obtains the session key along with the ticket. These are the two essential things which it obtains from the server S. So what it obtains is the session key KAB along with the ticket KAB comma A, which has been encrypted by KBS. So therefore you see that when this traffic comes to A, it can use this long term key called KAS and decrypt and obtain back the value of KAB. Along with it, it will also obtain the value of NA, be sure that this is not a replay and a new thing, and also this message, this entity B, which means that it is actually it is communicating with B itself, right, and there is no active adversary sitting between A and S. This is guaranteeing that fact, right. So now what it does is that it also obtains this ticket, and it is unable to decrypt this because KBS is not known to A, and it sends back the ticket to B. Now you note that B knows the value of the long term key, which is KBS, so it decrypts it, obtains KAB, which is the session key, along with the identifier A, right. Now what it does further is that it actually generates a fresh NB, which is again an n1s, encrypts it with KAB, which is the new session key, and sends it to A. Now what A does is that A decrements this NB minus and obtains NB minus 1, again encrypts it with KAB and sends it back to B. Okay. Now you note that this exchange ensures to B, or rather gives a guarantee to B, that this is a freshly generated key. Okay. And it also ensures to B that A is actually knowledgeable about KAB, right, that is A actually knows KAB, right, because whenever it decrypts and it decrypts by KAB, it knows that actually the thing which A has used to encrypt is the session key KAB, right. So it is a kind of key confirmation in the context of B, that B is confirmed that A is actually having the knowledge of the session key KAB. Okay. Now this is a very famous protocol and called as the Needham and Schroeder's protocol. Okay. So we see that stage by stage we can actually derive this Needham Schroeder's protocol. Now this protocol is actually a central, rather it is a central to what we know as the Kerberos protocol. Okay. So that is the next thing which we will consider, but before we go into that, let us consider yet another attack which can take place because of the communication between A and B. The attack could be like this, that is, the previous protocol assumed that only A can correctly answer the fourth challenge of B, right, but it may happen again that C may know an old key which is k dash ab, right. So therefore when B sends, I mean, so if you consider the previous protocol, this message was what, kab comma a encrypted with kbs, right. So what may happen is that C may come in between this communication and may instead relay this message, that is k dash ab comma a, which has been encrypted by kbs. Now you see that when B decrypts, it actually obtains k dash ab, which is again an old key, right. So therefore when it encrypts or does the freshness, it really does not solve the problem, right, because again we see that A and B, or rather at least B is actually obtaining an old key, right, which is again violating the objective of the protocol. So therefore we need to again change this protocol slightly, and the change is as follows: A communicates to S A comma B comma NA comma NB, and S communicates to A this message, that is KAB comma B comma NA encrypted with KS, and the other part is KAB comma A comma NB comma, which has been encrypted by KBS. Okay. So now when A obtains this first part, it can actually decrypt by using its long term key, obtain the session key KAB, and that is the idea. So therefore you see that this is obtained, and when it sends back this thing, so this message, that is the second part, then B again uses the key KBS and decrypts and again obtains back the session key KB, right. However, the previous protocol actually tried to do something more than this protocol. So therefore the previous protocol also tried to ensure that there is key confirmation for A, right. So but however this protocol is actually a lesser protocol, or actually obtains less, but obtains it in a secured fashion, right. The objective of a protocol is to actually state some objectives and achieve them, right, and if you state some objectives and you are unable to achieve them and actually open up some more vulnerabilities, then that is not a very safe protocol to use. Okay. So here you see that there is a difference between the previous protocols and this one. The difference is that the first message is actually initiated by B, right. So in the previous cases the messages were initiated by A, but in this case this message is initiated by B and then it has been communicated. Okay. So that is one change, or rather difference from between the compared to the previous protocols. So now let us see some of the discussions about protocol architectures, like it is. So therefore this is a very, I mean, well known fact that it is not possible to establish a new session key if you do not have a priorly developed knowledges. Like what I mean to say is that if you want to agree upon a new information, then there has to be some information which you have exchanged previously. Okay. It is a well known fact, that is, if I want to make a new session key, you have to assume that there is a long term key. So that is basically very central to the protocols that we are discussing. Okay. So therefore it is not possible to establish an authenticated session key without existing secure channels already being available. Now, and in order to do this establishment, you use servers. Like in the previous case, we have seen some cases of online servers, where the servers are actually part of the protocols. But in some other cases there may be offline servers. The offline servers may actually give something which is known as public keys and can distribute it among the network. Okay. So it could be like a public key infrastructure or a PKI as commonly called. Okay. So therefore there can be offline servers, there can be online servers, and depending upon that there are various kinds of protocols, right. So now let us see one very famous protocol which is used in distributed networking. It is called as the Kerberos protocol. Now if you have followed the Needham-Schroeder's protocol, you will see that there is a very strong application of the idea in this protocol. So here there is a key distribution center, and consider that there is a user client C who wants to actually use some application which is there in the server S. So in order to do so, it has to communicate with this key distribution center and obtain tickets. Okay. So tickets are kind of like will enable you to access a particular service. Okay. So what it does is that it first communicates with the Kerberos server. So the key distribution center is made of two servers. One is called the Kerberos server, the other is called the ticket granting server, or the TGS. Okay. So what the user client does is that it sends a request to this Kerberos server and asks for a ticket to communicate to the ticket granting server. So, this 2 actually is the ticket for TGS, for communication with the ticket granting server. Then the client actually communicates with the ticket granting server and does a request for the actual server ticket, like the ticket for the service which it wants from this server S. So, then the ticket granting server gives it back, gives the ticket to the user client. The user client then actually requests for the service and obtains the corresponding response of the service. So, this is the broad idea. So, you see that this is actually straight away an application of the Needham-Schroeder's protocol, because in the Needham-Schroeder's protocol also this was the central server and this was A and this was B. You can imagine like this. Okay. Similarly, when you are wanting to communicate with this, then this is A, this is B, and this is the central server S, right. So, you see the analogy, right, between the Needham-Schroeder's protocol and the Kerberos protocol. So, there are 3 phases in this, as you see. Okay. The first phase is like this: the user actually communicates with the client and sends its own identifier, which is U. The client then sends back to the to K, that is, so that you see that what we are saying is that we are actually dividing this user and the client into 2 entities. Okay. So, there is something like, you can imagine like I am sitting over a machine which is my which is actually the client and I am the user. Okay. So, the user logs into this client and wants to use this service, right. So, there is an amount of authentication between the user and the client as well, right. So, therefore, what the user sends, that what I send to the client is my own identifier. So, it could be in the form of a login, right, and what the client sends to K, that is the Kerberos server, is these 2 things, that is the identifier of the user along with the identifier of the ticket granting service where it wants to communicate with. Okay. So, on receipt of this information, the Kerberos server generates a session key which is called as KUTGS. So, KUTGS is the session key which is to be used by the user or the client to communicate with the ticket granting service. Okay. So, remember the previous Needham-Schroeder's protocol. So, the previous Needham-Schroeder's protocol imply that this Kerberos server has a key, has a long term key for the ticket granting service as well as a long term key for the client, right. So, therefore, these are the long term keys. So, the long term keys are, so there are 2 long term keys, right. So, you understand that there is one key which is the KTGS. KTGS means it is the long term key for of the Kerberos server for the ticket granting service, and there is another long term key which is the KU, which is maintained by the Kerberos server for the user U. Okay. So, what it does is this, that is, first on receipt of this information, the Kerberos server generates session key called KUTGS, which is to be used between the user and the TGS. So, the KUTGS is what? The session key. Okay. So, and it also creates a ticket TUTGS. So, that means that it is for user U to communicate with the ticket granting service, and the ticket actually comprises of the user U, the identifier of the user U, the TGS, which is the server of the identifier of the ticket granting service or the server, and also the session key which is KUTGS, along with the timestamp and the life of this ticket. Okay. So, there is a kind of life or an expiry date of this ticket. Okay. And this entire ticket has been encrypted by KTGS, which is a long term key which is maintained by the server K, that is Kerberos server, for the ticket granting service. Okay. So, KTGS is a key which is shared between K and TGS. So, it is again a long term key. TGS has previously an knowledge of KTGS. The ticket granting service is already aware of this KTGS. Okay. So, therefore, immediately when the ticket granting service receives this packet, it can actually decrypt this by KTGS and obtain the value of the session key KU comma TGS, right. And since this and when this Kerberos server sends to the client, it sends this KUTGS along with this ticket TUTGS along with this identifier of the ticket granting service and the timestamp and the life. It encrypts this packet by this long term key KU. So, therefore, again the client or the user is aware of this key. right, and therefore it will actually decrypt this and obtain the value of the session key, right. And the idea is that the client uses its key, which is generated from a password, which could be by a one-way function, and decrypts this corresponding message, and if this authentication is successful, then the client will store the session key, the ticket and other information for future use. Okay. So, it will store this ticket as well as this KU comma TGS for further use. Okay. So, therefore, what the client does now is that it has to communicate with what? With the ticket granting service, right, because it has to convey the convey what? Convey the session key to the ticket granting service. So, what it does is that it sends the TU comma TGS like this, because you note that this TU comma TGS is already encrypted, right. So, you do not need to encrypt it, and also the identifier of the server. So, now you see that it is sending the identifier of S, because S is now the service which it wants, right. S is this one, S is this service identifier. Okay. So, now when it sends this information to the TGS, it also sends that I want to actually communicate with the server and I want the corresponding ticket for communicating with the server, right. So, now what it does is that along with it, it also gives or generates an authenticator. The authenticator is very simple. It actually uses the session key called KUTGS. The session key means the session key between the user and the ticket granting service, and generates a timestamp along with its own identifier, that is the client's identifier, and sends it along with this message to the ticket granting service. Now, you see that from this ticket, the client the ticket granting service actually obtains a value of KU comma TGS, which is the session key, right, and it can immediately decrypt this authenticator, because this authenticator has been encrypted using KU comma TGS, and obtains back this value of timestamp, right, obtains the knowledge and gets the timestamp which has been used in this message, right. And therefore, when in the next message, when the ticket granting service communicates back with the client, it actually uses this timestamp to indicate again that it is a fresh message and not a case of replay which has been sent back, right. And therefore, you see that the corresponding ticket, now the ticket granting service is actually sending a message back to the user and sending what? Sending the ticket for communicating with the server along with the session key, which the user will actually use to communicate with the server, right. So, there are two things we are needed to be communicated, one is the session key and the ticket, the other thing is the ticket, right. And therefore, when it sends it, it will send this corresponding KC comma S and also the time, and along with the timestamp to indicate that it is not a case of the replay attack, and also the life of the ticket, right. So, this is actually sent along with KC comma S. What is KC comma S? It is a session key between the client and the server, right. So, there are two important things along with the S, which is the identifier of the server, along with the timestamp and the life, right. So, you see that everything has got its importance, right. The ticket has got its importance, every place where you are using the encryption also has got a meaning, right. So, on receiving this message, the client will decrypt and obtain the session key KC comma S and the corresponding ticket, which is TC comma S, which can be used for further request service from the server. So, immediately when C receives this, it has actually obtained the corresponding session key and also the ticket, right. So, now what the client will do is that it will communicate with the server S and it will send simply the ticket TC comma S along with an authenticator, which is again similarly generated like the previous authenticator, only this time you are encrypting by the corresponding session key, which is KC comma S, and encrypting the corresponding timestamp, right. So, the idea is that when the server receives it, it obtains the corresponding session key, and if it wants, you can again send back the authenticator, corresponding timestamp, so that it is again clear that there is again no case of replay between the client and the server, right. So, therefore, on receipt of this, the server decrypts the ticket TC comma S and obtains the session key KC comma S, which is used to decrypt the authenticator. The server S checks whether the message is fresh or not, right, because the server S can check whether the message is fresh, because it has, because you see that how the ticket has been generated, because the ticket also has a timestamp, okay, and the message that you are saying as an authenticator also has a timestamp, right. So, So, therefore, you can immediately understand that whether the authenticator also has a timestamp. So, you understand that the server S will check whether the message is fresh or not, because it can compare these two things, and see the life of the ticket. Okay. Right. So, the timestamp and the life are used to check that it is indeed a fresh message and actually prevent replay kind of analysis, right. So, this is the broad idea behind this kind of protocol attacks. So, therefore, you see that the previous three things, that is the three phases, like the phase 1 where you are actually obtaining a ticket for communicating between the client and the server, okay, and you are obtaining a ticket for communicating between the client and the server. I mean, the first one was client and the ticket granting server, second one is the client and the actual server, is actually based on the Needham and Schroeder's protocol, right. And essentially the objective of this protocol is to actually obtain the three important criteria. The three important criteria are essentially that an eavesdropper will not be able to observe. The second one is that there should not be any insider who can actually do an attack, okay, and even if the old key is being retrieved and I mean, even if the old key is leaked, right, it should not be again used. I mean, it should not be like the old key is again forced to be generated by the parties involved. And the other thing is that you are also ensuring that there is a kind of freshness in the keys that you are generating, right. That is, so these ideas are kind of related, but these are the important objectives behind a protocol of this nature. Okay. So, now you can have various varieties of protocols. You can have protocols which are two parties, three parties, multi parties, but the idea is that the objectives or the basic objectives are essentially the same, right. So, this Kerberos protocol was actually a part of a protocol, I mean part of a project which was generated by MIT. Okay. So, now there can be various modes of session key generation. There could be like things like key transport, where one principal generates the key which is transferred to the other. So, therefore, as we have seen in the previous cases were examples of key transport, because the session key has been generated by the server and it has been actually passed to both A and B in some form. There could be some other protocols where the session key is actually a function of inputs generated by all parties, like if there are two parties A and B and both actually gives some kind of a share, then that is used to generate a key. Okay. So, a classic example of that is something as we have seen is the example of the famous Diffie-Hellman protocol, where you know that there is a generator of this, there is a generator which has been previously established, and it could be like X. So, generator means generator of a finite field, okay, and or a finite group, and X is a member of this which is generated randomly, and B also generates Y which is a random share. Okay. So, what A does is that A computes this value of g power of x. This could be modulo a given prime number. Okay. So, and the other thing which can be generated by B is g power of y mod p, and what may happen is that this is communicated to B and again this is communicated to A, and now when g power of y mod p comes to A, it actually takes g power of y and raises it to this power of x, and what A does is that it takes g power of x and raises to power of y. Okay. And in both cases we know that these are the same. Okay. So, therefore, if you take a modulo p, then both of these are exactly the same. So, you see that here also we have actually generated a random number x and a random input y, and you are actually establishing a key which is g power of x y between these two parties, right. So, this is a classic example of a key agreement, okay, where key agreement between the parties A and B, where the session key is actually a function of the shares which has been generated by A and B. So, typically we can say that there is a function called f, and there A and B has actually contributed and generated like NB and NA, and the session key KAB is actually a function of both NA and NB, right. So, therefore, this function has to ensure that it is neither skewed towards NA or neither skewed towards NB. Both of them should have an equal contribution to the value of KAB, right, because what we will consider as a case of cryptanalysis is that I have a knowledge of NA along with some public information, can I obtain this value of k b, right. So, in this case, for example, imagine like if you actually know the value of x and you know the value of g power of y, then you know that immediately you can calculate g power of x y, right. But as a cryptanalytic point of view, you would be interested, like, because if there is an eavesdropper who observes this, then the eavesdropper obtains what, g power of x mod p and g power of y mod p, and it is interested to find out some way of computing the value of g power of x y mod p. So, this we have seen is believed to be a difficult problem, which is known as the famous Diffie-Hellman problem, right. So, therefore, the idea is that the function f should not be skewed towards either na or nb, okay, and it is typically a one way function, because it is also important that a knowledge of kab does not actually reveal the value of na and nb. So, therefore, we would like ideally at the end of the protocol also a and b should not be aware, like a should not be aware of, get a knowledge of y, and b should not get a value of x, okay. So, therefore, the typical requirement of a protocol or rather a function would be that it has to be essentially one way by nature, okay. So, there are some other protocols which are also hybrid. So, hybrid means that partially it is actually a key transport protocol and partially it is an actual agreement protocol, okay. So, therefore, it could be like partially the protocol is a hybrid, I mean it is actually a key transport, that is if there are two members a and b, then to a it is a key transport, but maybe to b it is actually an agreement, okay. So, there could be various kind of protocols as well, okay. So, let us see one example, we will see one example of a hybrid protocol. You can also categorize your protocols based upon the number of users. So, you can have, as I told you, like two party protocols or multi party, or which is also called as conference key protocols, okay. So, therefore, if you are going for conference key protocols, it will only complicate the matter a great deal, and there will be more other criteria and requirements which will come up, but the basic criteria that which we have seen already will still remain, okay. So, therefore, it will only make it like the protocols have to be more complex and it has to consider more practical scenarios and problems, okay. So, now let us see one example of a hybrid protocol. So, here there are again three parties A, B and S which is involved, and you see that A actually communicates with B and sends A comma Na, okay. So, therefore, A will communicate to B and send the value of A and also a fresh input which is generated and called as Na. Now, what B sends back to S is Nb comma A comma B comma KBS. So, you see that this is quite as we have seen in the previous case, right, the protocol as we have seen in the previous context, it is just one packet like that, okay. And so, there is a fifth protocol similar to that fifth protocol, okay. So, you see that this is being generated and sends, and B sends this to the server S. So, B actually sends it back to S, and what the other thing which it also sends is the corresponding value of Na, okay. So, Na is also the other thing which has been obtained from A, I mean B has received the corresponding entity from A and it has just relayed it back to S, okay. So, what S does is that S sends to a key which is called as KAB, which is a newly generated session key KAB, along with A, along with B, along with this fresh Na, and it has encrypted the entire thing by a long term key called as KAS, okay. So, and you note that the other thing which has been sent is this value of NS, okay. So, the NS is a fresh number which is being generated by the server, okay. Now, what A does or A sends to B is this NS, okay, along with A and B which has now been encrypted by KAB. So, you note one thing, that in this case the A has actually obtained the key, right, it has just got back the key from the server because it has been just transported to A, right, the key has been just transported to A and it has just got, it can simply obtain it by decrypting this packet by using its long term key called KAS, right. Now, what B does is that B sends again back to A KAB, I mean B comma A, which has been encrypted by KAB, but if you observe here that if you observe one interesting point here is that so far as B is concerned, B has actually not been provided KAB explicitly, okay, because B has never actually obtained KAB explicitly. You see that B, what are the messages B has actually got? B has a knowledge of NA, okay, and it has also got the knowledge of NB of course, and it has also got the knowledge of NS, because that is the thing which the server has communicated to B through A, right. Now, how has the server generated this key KAB? That is important, because that KAB has been generated by the server and communicated to A. Now, what the server does is that using its key or other part NS and the part NB, it actually applies a one way kind of function and obtains a session key called as KAB, okay. And this KAB is actually again can be generated by B, because B also has got a knowledge of NS and it has got a knowledge of NB, okay. So, B also has got a knowledge of NB of course, because it is its own key, okay. So, therefore, now it can again apply this function f and it can obtain the value of KAB. So, therefore, so far as B is concerned, B is actually not been given KAB explicitly, but it has been used to compute a function f by using it has been used by or rather generated by computing a function f, okay. So, therefore, to B it is an example of agreement, while for A it is actually an example of key transport. So, these are typical example of a hybrid kind of protocol, where to one party it is a transport and to the other party it is an example of a agreement, okay. So, the conclusion is that we have learned some basic tools to understand and build secure protocols. There is a huge literature on protocols, attacks on protocols, security analysis of protocols, and the idea is that clever and proper integration is very much necessary for a complete end to end security, okay. So, we have seen that we have to apply your basic encryption tools and basic techniques in a clever way and ensure that attacks are really I mean at least the known attacks do not work, okay, that is. And we can actually consider this problem. This is a problem which is known as the famous Haute East protocol, okay. So, here what A does is that A sends to B this messages m comma A comma B and sends this packet NA comma M comma A comma B, which has been encrypted by KAS, which is again a long term key. B sends to S M comma A comma B, and the second and this packet is NA comma M comma A comma B, which has been encrypted by KAS. The other part is NB comma M comma A comma B KB, which has been encrypted by KBS. The server S sends to B this M along with NA comma KAB, that is it has generated a session key KAB, encrypted it by KAS. The other part is NB comma KAB, which has been encrypted by KBS, okay, and B sends to A NA comma KAB comma which has been encrypted by KAS. So, this is a classic protocol, but you can imagine that if the lengths of NA comma M A and KAB are same, then there can be a potential attack against this protocol, okay. So, you can just think about this rather how the attack can work. As a hint, you can note that the first message and the second message, or the first and the fourth message has got a or the first and the third message has got a similarity, that is this part and this part. You can observe that this packet and this packet and this packet have all been generated by KAS, it has been encrypted by KAS, right. So, you can just think or ponder about whether this fact can be actually exploited for developing an attack, and also note that the adversary and the players observe the messages as bit strings and not as formal notations, okay. So, it will not observe this. So, therefore, if there is an attacker which can sit between the clients and it can actually send some bit strings which are not detectable by the receiver and can somehow fool this protocol, then there can be an attack, right. So, therefore, you can just consider whether this protocol is safe against a possible adversary. So, I have actually used this reference called Protocols for Authentication and Key Establishment by Colin Boyd and Anish Mathuria very extensively for this particular lecture. The 5-stage protocol you can actually find detailed in this book, and you can actually read it for more references. There is a huge repository of protocols present and is an excellent treatment on this subject. You can also refer to these other books which also have been used. So, you can find more reference on the Kerberos protocols in this particular text. So, next day we shall actually take up the topic on system security. Thank you.